Hello, this is a presentation of Fourth Planet Logistics on why the first humans on Mars will be cavemen, like the first humans on Earth. My name is Martin Gasser. I am a Swiss cave explorer and geologist with some deep Icelandic experience in volcanology and lava caves. My caving background is the Swiss Alps, where we have a big variety of caves with everything from huge vertical pits to lots of tight squeezes. Besides finding nice stuff on the other side of the squeeze, we explore caves in order to produce accurate three-dimensional maps of the underground passages that are accessible to man, at least to some specialists who are willing to spend weeks at a time underground. But let's see what we are going to talk about and what human spaceflight has to do with caving. We will discuss these topics here: why and how to live on Mars or Moon, what caves we can expect, and how we could use them. First, the journey to Mars. This is the so-called Hohmann transfer, the most energy-efficient way to go to Mars. The planets are turning counterclockwise around the Sun here, so if we had taken off from Earth down here in May 2018 on a Hohmann transfer orbit, we would hit Mars up there in January 2019. Then we have to stay on Mars for about 1.5 Earth years before the two planets are aligned again for taking the 6-month trip back home. Why do we choose the most energy efficient way for this journey, not the fastest one? It's not for protecting the environment, but because we will have a given rocket type that can carry more mass on a more efficient trajectory. So we will choose the most economic trajectory in order to be able to carry more beer. This is the usual artist's concept we always see of how humans will live on Mars or Moon. Some big landers with heavy heat shields, partly serving as habitats, with tube extensions, etc. We think this is pretty dangerous. That stuff all has to be shielded from radiation and meteorites and extreme temperature changes. Here is another one, and we think we should actually go underground. Here are some of the most important reasons, which I will go through one by one. These reasonings, by the way, were already made in the 60s, when human spaceflight first became a reality, but no caves were known at that time elsewhere than on Earth. This has changed today. In recent years, various cameras on different orbiters around Mars and Moon have taken high-resolution pictures of huge holes in the ground. This one is the biggest one so far on Mars, at about 400 meters diameter, comparable to the biggest vertical cave entrances on Earth. It's a collapse feature, not an impact crater, although the collapse could have been triggered by an impact. But in contrary to an impact crater, there are no rims, no ejecta, and generally vertical walls going deep down. The Mars Reconnaissance Orbiter has actually found an abundance of such collapse pits of different size and shape. These are just some examples. And on the Moon, it's the same thing. The Lunar Reconnaissance Orbiter also sent pictures of a variety of those pits. The Japanese too have an orbiter that has found vertical pits like this. We haven't confirmed any cave passages yet, but these pits might be the entrances to them. So, why should we go and live there? The most talked about reason is radiation. The Curiosity rover was measuring this. On transit, you will get about 2/3 of a sievert, and during 500 days on Mars surface, you get about 1/3 of a sievert, totaling to about 1 sievert for the whole trip. By living underground, we could lower this exposition by roughly 1/3. Sievert is a unit of measure for the health effect of ionizing radiation. 1 sievert is equivalent to 100 CT scans, which increases the risk of fatal cancer statistically by 5%. The next risk is dust storms. This is of course spectacular, and they do happen sometimes. But Mars' atmosphere is so thin, they will not knock you over like in the movie The Martian, although it was a good movie. But the dust will go everywhere, into your equipment, into every moving part, into gas processing units, filters, onto solar panels. The visibility will be low. The dust is nasty and poisonous to us, so it's good to stay out of a dust storm anyway. This is a depiction from a National Geographic movie. There is a global dust storm actually raging on Mars in 2018. This is a telescope picture from end of June. This storm has stopped the Opportunity rover because it runs on solar. It went to sleep to sit out the storm and has not woken up yet. You see the haze spread around the whole planet quite well on this picture. For me, the most interesting is meteorite protection, because I like meteorites, but not on my head. They are quite common even on Earth, although the Earth is shielded by a thick atmosphere that burns up meteorites, which are smaller than about the size of a car. But the bigger ones will fracture and pieces of them will make it to the ground. They even form craters sometimes, but the probability to be hit is small enough so we don't wear helmets all the time. But one person, this lady here, is actually known to have been hit directly by a meteorite. It fell through her roof and hit her on the body, but she survived. I'm going to argue that on Moon and Mars, the probability to get hurt by a meteorite is much higher than on Earth. This is one of the one-to-one observed impacts on the Moon. It's a flash of light in the upper right of the picture. This was the brightest one so far observed from Earth. And these are the calculated data from this impact based on brightness and duration of the flash. It was a rock of about briefcase size, and they impact often enough so that people looking through their telescopes sometimes see them by accident. The dangerous thing is that they come in at tremendous, unimaginably fast speed. It was written here in some fantasy unit nobody uses anymore. I think it was miles per hour or so. So I changed it. Meteorites typically hit at speeds around 25 kilometers per second, also on Earth. This is more than 20 times faster than a bullet, which means a bullet at that speed would have more than 400 times more impact energy. The Moon has no atmosphere to slow anything down, so this rock was fast enough to explode upon impact and evaporize to a fireball of glowing gas and dust, visible even from Earth. If you would have just a pebble hitting your habitation at that speed, it would go right through and destroy everything. On Mars, new craters are found from time to time at places where there was no crater before. These pictures are all from places from where we had an older picture without a crater. There are about 200 such impacts per year on Mars. This means on average for each surface area the size of California, there is one new crater formed each year. And if a meteorite impact forms a crater, it's quite a bit bigger than the one that will destroy your house. The smaller meteorites, the more frequent they are in the solar system. So I would count this as a significant hazard for permanent dwelling. On Mars, the thin atmosphere filters out at least the smallest meteorites, but on the Moon there is no atmosphere at all, and every grain of sand will hit at around 25 kilometers per second. The next very important thing are stable temperatures. On Mars it gets very cold at night, and the length of day is almost the same as on Earth. On this diagram we see temperature changes throughout the day and throughout the year for Mars and for Los Angeles. We see that the temperature difference between day and night and also between summer and winter is much more extreme on Mars. This is bad for your equipment, especially for airtight joints and seams, and everything also turns brittle at very cold temperatures. But in a cave with air circulation, we could expect a temperature close to the overall average of outside temperatures all the time, something like the purple line here. It's a bit cold, minus 50, on the Moon minus 30, but in the Antarctic people dwell in this environment quite successfully. Here is an example from Iceland to show how sharply the climate changes from the surface to inside the cave. You see the icicles melt at their tips. The most important technical issue is that we cannot bring very much stuff. We don't want to carry heavy shielding, we don't want to carry bulldozers to build shielding on site. We just want to go into a cave. Here is a drawing that I made of how this could work in a small cave. Some sort of robot, here a spider robot, yet to be designed, brings a hab into a cave and inflates it to the size of the cave at 1 bar pressure, using the cave walls as a structural element. You can add to the redundancy of safety by sealing the cave walls and pressurizing the whole gallery around your hab. And when you're finished, people could just come and move in right away. In bigger caves, we cannot use the walls as structural element, but we can put up inflatable habitats on the floor. This will be sort of like living in a mixture between a submarine and a balloon. This is an architect's concept for fourth planet logistics. And if you have enough 3D printers and when you're capable of living off the land, of using the regolith as a resource, you can imagine building ramps and lightweight domes or whatever you need. The most important scientific reason and a possible source of government money is the possibility to find life in caves. Maybe you know this meteorite, Allen Hills 84001. It's indeed from Mars. It was found in Antarctica and contains some worm-like features. They are 1 order of magnitude too small to resemble any living creatures we know of. But there are also micromagnetite crystals that are arranged in a way organisms would do it. But the evidence is not conclusive enough to be sure that these are fossils of living organisms. It is just a proof that there are strange things going on in rocks on Mars. Nevertheless, this is enough motivation to look further. There is research done underground on Earth. Judd Winnie, who also did research on finding caves on Mars with infrared, he investigated caves in vertebrates in lava tubes on Rapa Nui. What he found was species that had long gone extinct on the surface but persisted underground, so-called vestigial life forms. This shows that in an isolated ecosystem like a remote island or a remote planet, the underground can conserve living species even after drastic and deadly changes of the conditions at the surface. Penny Boston is a renowned underground biologist affiliated to NASA, and she is also excited about going to Mars. One of her fields of research are underground microbes, and she finds an abundance of them, not only in caves but also just inside the rock itself, up to several kilometers deep underground. Remarkable is a huge genetic difference between underground and surface microbes, and a big variety between the subsurface microbes too. This indicates that the evolution of life in the subsurface is quite independent from what is going on above ground. My lovely wife, she has done a study on fossil subsurface life forms in eastern Iceland. She was looking for biosignatures in chert, an SiO2 mineral, here in the variety of red jasper. Under the microscope, this is not red at all, but colorless, and it has these things here that just look like biomats. So they are most probably biomats. Biomats could have lived in hot water under hydrothermal conditions close to a volcano and were silicified later on. Looking closer, we see that these fibers look exactly like recent iron bacteria, Gallionella for example. Icelandic rock and Mars rock are very similar, so it is thinkable that we could find fossil life on Mars in this form. So what are those caves I keep talking about? They are lava tubes which form during volcanic eruptions. When basaltic lava erupts slowly onto a gentle slope, it often forms large flow fields that crust over because the lava cools at the top and solidifies. And this crust is a very good insulator, so inside the lava stays liquid and keeps flowing. To the right is an aerial view of such a flow in Hawaii. There are trees for scale, and in the middle of the lava we see openings in the crust, so-called skylights, with red-hot liquid lava visible inside. And as any other liquid flowing down a slope, the lava gets channelized like a river system and flows in tubes inside the lava flow, so-called pyroducts, or colloquially spoken, lava tubes. On the left is a map of such a lava discharge system. At the end of the eruption, or when a tube gets clogged, the remaining lava flows out of the tube and leaves behind a cavity. The glowing skylights in these pictures are often the entrances to such lava tubes. Now it's important to say that not everything that looks like a skylight leads into a lava tube. These are tectonic cracks on Mars formed due to expansion of the crust, and they also show circular collapses like these. In several publications, collapse pit chains like these are mistaken for skylight chains over a lava tube. However, no reasonable geologist should make this mistake. I have descended into several tectonic cracks for research, and I don't recommend it to anyone. It is way too dangerous. If you touch anything, it can fall, and if you look up, a rock can fall into your face and make you ugly or dead. Tectonic cracks are intrinsically unstable and full of loose rocks, and therefore not our target. What we want is a nice passage, a gallery to walk, like in this comparison between an active and a habitable lava tube. They can also collapse, but the loose rocks have normally all fallen down already due to earthquakes. So they are safe enough to get in, for example, to get married inside. This is a special case of a lava tube that has formed inside a tectonic crack. It is safe to get in until the crack gets reactivated. But we have to expect that the entrances to most lava tubes are vertical, so we have to use vertical speleological techniques in order to get in. Now, if we look at such pits on Mars, we see a striking similarity to the cave entrances on Earth, and it's easy to imagine that there is a gallery leading away from the pit underneath the surface. But where and how can we find the right cave? One very promising method is infrared satellite imaging. The resolution is a limiting factor here, and with the currently orbiting instrument THEMIS, only the biggest pits can be detected. To the left, we have a daytime visible light image. In the middle is a daytime infrared image, where the cave is a cold spot, but it does not really show up. The right time to watch with infrared is towards the end of the night, when the surface has had time to radiate its heat away. So the picture to the right is such an image, and we readily see the cave light up as a hotspot in contrast to its very cold surroundings. We can look for caves on the flanks of volcanoes like Arsia Mons here, and at places where we have signs of flowing lava like lava channels, for example. On the Moon, such channels are called rilles. The famous Hadley Rill was visited by Apollo 15. There are very similar rilles on Earth in lava fields that contain caves. The Japanese probe Kaguya has discovered a very promising pit in a rille on the Moon. Here is a close-up of the pit, showing how it sits in the middle of the channel close to a bend. But we don't see the bottom of the hole. Here are 3 pictures of this pit with the sun at different angles, and obviously we only have a good view of the floor when the sun shines down almost vertically, unless we use photographic tricks. But the best view turns out to be with a camera at an oblique angle and the sun at the zenith. Here the overhang is finally visible, a gap between the ceiling and the floor, which points to a possible passage continuing underground. So this is very exciting. This is another moon pit, for as an example, found in Mare Tranquillitatis, which has also been described in some detail in the literature, and there are many more examples already. Now, there are 2 pits on Mars that I have looked at more closely. They are situated in a vast lava field in the Tarsis region close to Ascraeus Mons. This is the original view here to the right, and the most striking features are these fuzzy streaks of dark material whose origin is obviously in those holes. We see 2 or even 3 different wind directions in which the dark material has been blown out of the pits. I found this picture on the HiRISE homepage. HiRISE is the high-resolution camera on the Mars Reconnaissance Orbiter. This is a zoom on the 2 pits. It's a very high-resolution image, and I think it was the best image of any extraterrestrial cave at the time. Because what they could do was to overexpose the pits in order to see some contrast inside. This was very successful, and in the next slide we will see down into the bigger of the 2 holes. This is the view, and I found it very striking. But the description to these pits on the web page was very bad, even wrong. So I decided to make a better description. That was in 2010, and this is how I began to get active in this topic of extraterrestrial speleology. The resolution of the picture is so good that we can distinguish columnar jointing in the walls, typical for lava, and elongated rocks, lava columns that have fallen from the walls to the ground. Here we have the smaller one of the 2 pits, with a special shadow pattern on something that looks like a sand dune. With the data to the pictures that are all listed on the HiRISE webpage, like emission angle and solar incidence angle, and with the shadows, I could construct an approximate cross-section of the pit here to the right. We see the sand dune on the floor here, and the Sun and the satellite, who are almost opposite of each other. This is again the bigger hole, with some of the geometrical constructions and with the inferred cross-section to the right. In the cross-section we see that the depth is roughly the same as the width, which is 300 meters, and the passage that could lead from it could easily be 100 meters high. This corresponds to the darkest area in the picture. This is the same view again, just in better quality. This is a newer view of the same hole from right above. We see here quite well that the scree on the floor has come from the walls, and there is not very much of it. So the bulk of material from the collapse of the pit no longer seems to be there, and probably has been carried away when the lava flow was still active. As in this example from Mount Etna, where we see that everything that falls down here gets carried away by the heavy flowing lava. We also see the scale here with a person standing on top. As in this view here of another typical well-manageable skylight on Earth. The scale is very different on Mars due to lower gravity. This is a Boeing 747 photoshopped to the side of a typical Mars pit. But we hope to find more smaller ones in the future with better resolution imagery. Here is a collection of Mars pit with scale bars, and you see that in the smallest one you probably even could just walk in. Now a little bit about techniques to get in there. For humans, we will use more or less the same techniques as in terrestrial caves, but beforehand we want to send robots to find and survey the right cave, and preferably even prepare it for habitation. I have taken this part from a very nice presentation by a guy called Red Whittaker, who is also very excited about going into caves on Mars. He is a robotics professor and has a company called Astrobotics, which is actually building such landers and rovers as depicted in these cartoons. This is his concept of how a robotic cave survey on Moon or Mars could work. So we see a lander coming in here and taking close-up navigation pictures of the pit, shown here in cross-section. And it lands in a safe spot nearby, drives up to the pit and deploys 2 rovers. One rover is lowered down into the cave on a cable, the other one serves as a communication relay on the surface. Then the underground rover starts the survey of the cave. These data are just length, angle and width. Very simple and can be sent via low bandwidth connection directly through the rock to the relay. This is also done in cave rescue operations on Earth. The data can be sent to Earth from the surface, and the survey can continue. Sometimes a command may be sent from Earth to turn right, for example, and at some point there will be a return command and the rovers will get back to the cave entrance. When it is back at the entrance, it can send photos it has taken of the cave through a high bandwidth cable connection to the lander and from there via high gain antenna to Earth, where we will be able to do photogrammetry and build an accurate model of the passages. This is one possible way of doing a robotic cave survey, but there are several other possible methods, like inertial navigation systems, or swarm robots, for example, or for bigger caves, flying drones could be used, at least on Mars. Research and development is on its way, and this is one of our goals to find out what is the best robotic method to survey extraterrestrial caves. Here are some challenges for the idea of using caves as habitats. First of all, NASA is scared of slopes. They don't want to land on anything steeper than 30 degrees inclination, and they are also scared of blocky terrain. Caves are very blocky terrain and usually very steeply inclined. And NASA as a government agency could realize the Apollo program, for example, only because of the Cold War and the space race with the Soviets. Nowadays it has lost the capability of sustaining big and expensive projects for longer than an election cycle or two, and will not go to Mars in the next 50 years, I guess. But there are all these private companies who have begun a new space race just in the recent years. SpaceX, for example, has been founded with the goal of going to Mars. These companies are very powerful and motivated to go to Mars, and they will be willing to find out the cheapest and safest way to keep people alive for longer time periods on Mars or on Moon. They also pursue a fruitful collaboration with NASA and other space agencies, which is good for enhancing know-how and cash flow on all sides. The moon landings were done half a century ago, and they were probably the greatest and most inspirational achievement of mankind. This spirit has gone forgotten in past years and decades, and it is our generation and this kind of extremely wealthy entrepreneurs that can keep it alive and inspire the kids and awaken humans' natural curiosity to finally just go there and see how it is to be there. No robot can give that to us. Another more technical challenge is that caves are not everywhere, and on Mars they tend to be associated with mountains and higher terrain where it's difficult to land because of a lack of air to slow you down on the way in. And horizontal cave entrances, the most desirable ones for our purposes, are notoriously hard to find from above. For this, a low-flying drone would be helpful. And the last challenge I want to mention is the critical mass of people or of incentive that has not yet been reached. This means that already a lot of experts and actors in the field more or less independently came to the conclusion that it would be most reasonable to dwell in caves while on Mars and Moon, but these individual actors only have little influence on whole space programs. So they should be better coordinated with one another. For example, they sometimes don't know if they should compete or collaborate together. This is where Fourth Planet Logistics comes in. This is a screenshot of the website. This company was founded in the aftermath of the Explorers Festival in Iceland in 2016 by an American, Michael Dunn, to the left in this picture, together with the president of Iceland and astronaut Scott Parachinsky. I was the caving guy at this Explorers Festival, and I was approached by Mike and Scott if I would like to help them route a climb on Olympus Mons on Mars, the highest mountain in the solar system. How could I say no? So one thing led to the other, and later Michael Dunn founded the company Fourth Planet Logistics with the goal to create and test underground habitats in real lava tubes on Earth in order to develop the methods to build such structures on other planets. There is a cave in Iceland called Stefánshellir, for which we have obtained the necessary permissions to use it as a test site. All the nice features in the cave, mostly lava stalagmites and stalactites, have been destroyed and stolen throughout the years, which is very sad. But good for us, because if we go there, we won't damage the cave anymore. Cave protection is very important because untouched caves are an extremely sensitive and rare and precious environment that is susceptible to every visitor from outside. Here is an aerial picture of the cave area. It is a 1100-year-old lava field in Arctic climate with only moss as a vegetation cover. Of course, we want to have as little vegetation as possible in a Mars analog, so this is good. And there is also seasonal ice inside the cave, which allows us to test how possible permafrost on Mars would react to a habitat that will inevitably be heating up the cave. The cave has several entrances of different sizes, giving us several possibilities to test ingress and egress. The most conspicuous circular vertical entrance is at the very top of the picture. Here is a close-up of another entrance. This was in April. The cave is only readily accessible in summer. In winter you have to dig through the snow. The entrances often get filled up to the rim by snowdrift. But there could be a base inside the cave throughout the year because of aforementioned stable temperatures and absence of dust storms inside the cave. This is inside the cave. In winter there are some ice draperies close to the entrance. There is a variety of different passages. The one to the right is good for trying out inflatable habitats, for example. And this is where we are going next in order to test the testing. Thank you for your attention and stay tuned for updates.